Today, I will be going over Lab 3, which is about black hole. The purpose of this lab is to use the provided limited knowledge from the glow script to calculate the mass of the black hole. This is for part 1, and then part 2, we use the black hole's mass to calculate an initial velocity for a ship to not crash into the black hole while getting as close to it as possible. For the setup of this lab, there's no actual experiment for this lab, like previous labs. Instead, we are given two starter glow scripts to work on to calculate the mass of the black hole and the initial velocity of the ship. A couple equations that we used in this lab. There's a lot more equations used, but these are the important ones. Of course, the momentum update and the velocity update formula that we used in part 2 to update the ship and the planet. Newton's second law, of course, and the force of gravity formula are also used to calculate the mass of the black hole and help with the initial velocity of the spaceship. So for part 1 of the project, we estimated the mass of the black hole. You can see from my glow script here that I will also link to the video in the description that different mass of the black hole at different points of the orbit are calculated by calculating multiple variables as shown above. There's actually a lot of those, such as delta V, delta P, dp dt, fnet parallel, perpendicular, and then after plugging in all the formulas, we were able to get a black hole mass for like every second. And we have to average all the black hole values to get the best estimate for the mass of the black hole that we used in part 2 of the lab. So for part 2 of the lab, we had to choose a correct initial velocity of the ship to avoid crashing into the planet and the black hole. So first we have to calculate the different forces acting on the ship and the planet, and then testing out multiple values of the ship speed. I was able to set the ship to appropriate speed that the ship gets close to the black hole but doesn't hit it. You can see on the right there's a picture of the graph. I mean, the visual representation of what exactly happens. The purple pink line is the ship, and it gets close to the black hole, but then it gets away and doesn't hit the planet or the black hole. Okay, and now we have one of the questions that was in this lab. So the question is about how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. My answer for this question is that the rate of change of momentum in our scenario will have the same parallel and perpendicular components as the net force. This is because the momentum is equal to mass times velocity, and the rate of the change of that is mass times acceleration, which is the same as the net force. Question 2, what if? So for question 2 of the lab, it asks for what initial velocity would your spaceship need in order to enter into some kind of orbit around the hole? Well, for part 2 of the project, my spaceship actually escaped the the hamburger between the planet and the black hole by by doing a really fast, and it escaped the hamburger before the planet started orbiting the black hole. So in order for the spaceship to enter some kind of orbit, it would have to be lower. Its initial speed would have to be lower than what I had in part 2. The orbit will therefore be a smaller circle than the planet orbit in the scenario. This will ensure it crashes neither into the black hole or the planet. This velocity will also need to ensure that the resulting net force is big enough to keep our spaceship in orbit. And this concludes my presentation over Lab 3, Black Hole. Thank you for listening.